Here's my approach to the problem. Here's our axes. Here's my function, f of x. And now the problem is I'm given some value of y, and I want to find the value of x that corresponds to that, such that f of x equals y. And the strategy we had before was to just start at the 0 point and go out step by step by step until we found it. But that's going to be slow if there's lots of steps. So my approach is going to be, first I'm going to take one step forward, and then if the value of f of x is still below y, then I'm going to double how far out I go, and I'm going to keep on doubling how far out I go and checking. So 1, 2, 4, 8, 16 units out, and until I've got bounds. So here I have this value that I doubled, f of x was less than the desired y, and when I went all the way out to here, f of x was greater than the desired y. So I know that the right x has to be somewhere within this range. So that gives me the low and the high that I get by doubling, and now I'm going to find the exact value, or close to the exact value, within low and high by halving. So first doubling, now halving. So I look in here, say what's halfway between low and high. That's at this point. F of x there is still too high. Now I know I must be somewhere in this half. I go halfway there. That's still too high. Now I know I must be in this half, and I keep on doing that process until I zero in on the right value. That's the strategy. Now let's see what the code looks like. So here's my function inverse. I'm going to have my smallest delta, the smallest amount that I move out, be 1 over 1024. So that's going to get me to within 3 significant digits. And I'm going to build up this f inverse function. So I was given y equals f of x. I'm going to build up x equals f inverse of y. And I do that first by finding the low and high bounds. It's got to be somewhere in there. And then doing a binary search somewhere in between that low and high to find a value that's accurate to within delta. Here's how I find the bounds. I start off and I just keep on doubling until I find a value that's high enough. So what I keep on doing is narrowing down the interval between low and high until they come out to be the same, until the interval has disappeared. If I'm too high, then I change the low. Otherwise, I change the high value. That makes the interval smaller and smaller. If I hit it exactly, I go ahead and return the x value. If I haven't hit it exactly, then I know I'm somewhere in between the two, and I just check out which one to do. Now I've defined some functions here to help me test what I've done. I've defined the square and the 10 to the x functions, and now I define those inverses. The logarithm is just the inverse of the power of 10, and square root is the inverse of square using the function I defined. I can also do cube root is the inverse of the cube function. And then I'm defining some tests. So for these sets of numbers, I'm going to test these functions, square root, log 10, and cube root, and I'm going to test them against the correct mathematical functions as defined by Python. These are the ones I've defined with inverse. These are the ones Python defines. And here's my individual tests. And here's what I get when I run the test. So for each of the numbers, for each of the functions, here's the result I compute with my inverse function. Here's the actual results. And you can see the differences are all in the 0.001 or less. And that's true for small numbers, and it's true even as we go up to bigger numbers, like 10 to the 8th.